At each electrode-electrolyte interface, there is tendency of metal ion from the solution to deposit on the metal electrode, trying to make it positively charged. At the same time, metal atoms of the electrode have a tendency to go into the solution as ions and leave behind electrons at the electrode, trying to make it negatively charged. At equilibrium, there is a separation of charges. Depending on the tendencies of the two opposing reactions, the electrode may be positively or negatively charged with respect to the solution. What happens when zinc from the zinc electrode goes into the solution as Zn2 plus ions? Then solution is positively charged, but the zinc electrode is negatively charged. Similarly, in case of copper electrode, when Cu2 plus ion from the solution take electrons from the copper electrode and deposit on the copper electrode as copper atoms, then since Cu2 plus ions have taken electrons from the copper electrode is positively charged, and as the solution has lost some of Cu2 plus ions because they have changed into copper atom, the solution is slightly negatively charged. So the electrode may be positively charged or negatively charged with respect to the solution. So a potential develops between the electrode and electrolyte, and this potential is called electrode potential. When concentration of all the species which are present in the half cell is equal to 1, then the electrode potential is known as standard electrode potential. According to IUPAC convention, standard reduction potentials are now called standard electrode potential. Means if standard electrode potential of any electrode is given, then it is the standard reduction potential. Standard reduction potential means potential to get reduced. In a galvanic cell, the half cell in which oxidation takes place is called, this is anode, it is called anode, and it has a negative potential with respect to the solution. The other half cell in which reduction takes place is called cathode, and it has a positive potential with respect to solution. Positive potential with respect to solution. Thus there exists a potential difference between two electrodes, and as soon as the switch is in the on position, the electrons flow from the negative electrode to positive electrode. Flow of electrons is from the negative electrode to the positive electrode, and the direction of the current flow is opposite to that of electron flow. Now potential difference between two electrodes of galvanic cell is known as cell potential, and it is measured in volts. It is the difference between the electrode potential, that is standard reduction potential of the cathode and anode, and it is represented as E cell is equal to ER minus EL. Right hand side electrode is the cathode and left hand side electrode is the anode. So subtracting the reduction potentials of anode from cathode will give the cell potential. And if no current is drawn through the cell, then the cell potential is known as cell electromotive force. While representing a galvanic cell, anode is on the left hand side and cathode is on the right hand side. And how is a galvanic cell represented? This is the representation of galvanic cell. Metal is separated by a single vertical line from the solution of its ions, that is from the electrolyte solution. Two electrolyte solutions are separated by two vertical lines. These are the two electrolyte solutions which are connected by salt bridge. And then again metal ion or the solution of metal ion, that is the electrolyte solution, is separated from the metal by a single vertical line. Now this is the cell reaction for the galvanic cell represented. Copper is getting oxidized. So copper is undergoing oxidation. So copper acts as the anode. This is the oxidation reaction, oxidation half reaction. Silver is getting reduced. Silver is acting as the cathode, and this is the reduction half reaction. And EMF of the cell can be written as E cathode minus E anode. E cathode, silver is acting as the cathode, so reduction potential of cathode minus reduction potential of anode. Since reduction potential of anode is used in calculation, it is represented as ECU2 plus 2Cu. The EMF of the cell is written as reduction potential of cathode. So cathode Ag plus ions changing to neutral silver atoms minus reduction potential of anode. So the reaction taking place at anode is oxidation, but since the electrode potentials are reduction potentials, here for anode also reduction potential will be considered. Therefore, it will be represented as Cu2 plus changing to Cu. Copper ions getting reduced to metallic copper. Now, potential of individual half cell cannot be measured. So, there is a need for a standard electrode, and this standard electrode is a standard hydrogen electrode. This is the construction of a standard hydrogen electrode. This is platinum electrode which is coated with platinum black, and this is a acidic solution. Hydrogen gas is passed through this acidic solution. Pressure of hydrogen is maintained at 1 bar. The concentration of the acidic solution is 1 m, and the standard hydrogen electrode potential is taken as 0. And this is the representation of the reaction which is taking place at the standard hydrogen electrode, that is H plus ions accepting electrons and changing into hydrogen gas. Now when standard hydrogen electrode is used as reference electrode, usually the hydrogen electrode is made the anode. Now when calculating the cell potential is equal to E cathode minus E anode, and since anode is a standard hydrogen electrode whose electrode potential is taken as 0, therefore value of E anode will be 0. So cell potential will be equal to the reduction potential of the electrode taken. So the value of electrode potential of a given electrode when it is connected with standard hydrogen electrode will be equal to the cell potential. Whatever will be the value of the cell potential, same will be the value of electrode potential of the given electrode which is connected with the reference electrode. For example, when copper electrode is connected with standard hydrogen electrode is acting as anode, copper electrode is acting as cathode. This is the cell reaction taking place. So EMF of the cell or cell potential is equal to E cathode minus E anode. Now standard reduction potential of hydrogen is 0. So EMF of the cell is 0.34, and this is equal to standard electrode potential of the cathode. So standard electrode potential of copper electrode will be equal to 0.34 volt. Similarly, when hydrogen electrode is connected with zinc electrode, the value of cell potential is equal to minus 0.76. So it can be written as E cathode minus E anode is equal to minus 0.76. Since E anode is equal to 0, therefore E cathode, that is the value of electrode potential of the zinc electrode, is equal to minus 0.76. Now positive value for the standard electrode potential of copper. For copper, the electrode potential is plus 0.34 volt. Means copper ions, they have greater tendency to accept electron and get reduced to copper atoms in comparison to H plus ions. Therefore, H plus ions cannot oxidize copper. It is not possible for H plus ions to oxidize copper to Cu2 plus ions because Cu2 plus ions have greater tendency to accept electron in comparison to H plus ions. So copper will not dissolve in HCl. Copper will not dissolve in HCl. Why? Because here in HCl H plus ion is present, and this H plus ion cannot oxidize copper to Cu2 plus ion because Cu2 plus ions have greater tendency to get reduced in and change into copper atom in comparison to H plus ions. So it will not be able to oxidize copper to Cu2 plus ions. Or it can also be said that hydrogen can easily reduce Cu2 plus ion to copper atoms, and hydrogen itself gets oxidized to H plus ions. Since the standard reduction potential of copper is 0.34 and standard reduction potential of hydrogen is 0. So standard reduction potential of copper is greater than hydrogen, as a result of which standard reduction potential of Cu2 plus ions is greater than H plus ions, because of which H plus ions will not be able to reduce Cu2 plus ions, and on the other hand Cu2 plus ions can be easily reduced by hydrogen and change into neutral copper atoms. Thus copper does not dissolve in HCl. In nitric acid it is oxidized by nitrate ion and not by hydrogen ion. In nitric acid also there is H plus ion and NO3 minus ion. Still copper changes from copper to Cu2 plus ion, but this is because of the nitrate ion, not because of the H plus ion. H plus ions cannot oxidize copper to Cu2 plus ions. The negative value of standard electrode potential in the second case, that is in case of zinc, indicates that hydrogen ion can oxidize zinc. Now for zinc, Zn2 plus changing into zinc atoms, this value, reduction potential value for zinc is minus 0.76, means it is less than hydrogen. Reduction potential value of zinc is less than hydrogen, means in comparison, when we compare zinc and hydrogen ions, then H plus ions have greater tendency to get reduced. H plus ions have greater tendency to get reduced, so they can easily oxidize zinc to Zn2 plus ions.